Hello, it's December 22nd, we're getting very close now. And what I want to talk about today is basically the only Nobel Prize that was awarded for accelerator physics that I know of. And this was awarded in the early 1980s to van der Meer, and it was for a process called stochastic cooling. Now the reason stochastic cooling is, well, cool, is because it uses very, very simple ideas and basic geometry to overcome one of the biggest problems we face in modern particle physics. And that's the following. Let's say you have a particle accelerator and you're taking particles from one energy, accelerating them to very close to the speed of light and taking them somewhere else. You need to be able to contain that beam. And to contain that beam of particles, you need to be able to measure what the particles are doing. As you measure what the particles are doing, you know what they'll do in the future, and then you can change what happens further down the beamline to take this into account. So let's say you have particles down here, and they're starting to veer upwards. You want to be able to correct this and say to the magnets downstream, kick the beam down, so it'll go back where it should do. Now the problem with this is the particles are going almost at the speed of light, and the fastest you can send a message is at the speed of light. So you have your particles coming along here, they're going up slightly, and you measure this, and then you send the message at the speed of light over to here, and you hope to get there before these particles do, to tell the magnet to kick them back into position. And when you work out how much time you've got, it turns out you don't actually have enough time to configure all the electronics, to actually measure something here, send the message across, tell this magnet what to do, and actually get the magnet to change its field in time. Now what van der Meer did was create a circular accelerator. And the really clever thing here is now the particles got to go all the way around, whereas you can send a message across the diameter of the circle. So you send the message across 2 times r, where r is the radius, and the particles are going 2 pi r. And so you take the difference, and this difference is then pi times, so pi minus 1 times 2r. And this gives you enough time to actually change your magnets, to change the fields of them, and to change their strengths. And this was known as stochastic cooling, and this got the Nobel Prize back in the early 80s. And to me, it is just a fantastic example of how you can use a very simple idea, just the geometry of a circle, to overcome one of the most advanced problems that science has ever faced. How do you send messages at the speed of light to get somewhere before particles going at nearly the speed of light get there? How do you actually do that with enough time to make the changes you need to make? And van der Meer did it. He used very simple, high school level geometry to solve this problem. That's really cool. Okay, I'll see you tomorrow. I think my favourite treat at Christmas was the chocolate pennies. And for a long time I just thought they had pretty patterns on. So I was really happy when I finally got to Switzerland to work at CERN to find out that these are actually based on Swiss money. So we have here the 5 franc piece, and I know which one I'd rather have. And of course we have the other francs. We have the 2 franc piece. And what do we have here? The half franc. Oh, is this it? Do we have any more? Oh, there's a 1 franc piece. And 1 franc piece. I think that's all we have. Yeah, so there we go. I don't know if you have these in the USA, but this is exactly what I used to get in the UK. And it took me until I was about 28 before I actually got my hands on a real 5 franc coin. And this of course reminded me of Christmas and chocolate.